Let's start with the free body diagram. Can someone tell me one force that's acting on this box? One force that's acting on the box. Let me make some room so we can. Raised hand. Nor, go ahead.
The force of gravity.
I love that. That's a good choice. When we do this, we start with a dot on the center of mass, like so. And then we take an arrow and we draw from the arrow for the center of mass directly downwards for this case. Actually, I'm just going to make a new arrow because it gets kind of funky that way when I do it that way. Take this like so, and right straight down, we got ourselves the force due to gravity, Fg. If you need to calculate the force due to gravity, you take the mass of the object and you multiply it by g, and where g is 9.8 newtons for every kilogram, the gravitational field strength, right? The gravitational field strength. Yeah, so far so good. Sebastian, did you want to add something to it?
No, I was gonna say
No.
the same thing.
Just you were going to say the same thing. Okay. Any other forces acting on this block? Amir.
Normal force.
Good. The normal force. Which direction does the normal force point?
Upwards.
Like so.
I think so.
Does anybody remember why it's called the normal force? Why do they call it the normal force? Who knows why it's called the normal force? Michelle, do you know why it's called the normal force?
Yes, it makes a 90-degree angle.
Ah, it's called normal because it's makes a 90-degree angle with the surface, right? Is this one as is making a 90-degree angle with the surface?
No.
No, right? So they're close. You're in the right. It's in a upward-ish direction, but it's not quite. It's bent over to the side. Something close to this. Now, for us to maybe work this out easier, I'm going to set up a coordinate system that makes it easier to kind of track things that are perpendicular and things that are parallel. And there's a reason for this. The reason is it basically helps us track the motion better. Because the block, right, in this situation where it's a frictionless incline, the block is going to head in this direction, right, like down the incline. And I'm just going to, I want to make it look like a train track if I can. That looks pretty train tracky to me. Right, so the block is going to, let's make this gray really faded so it's not in the way. The block is going to accelerate. Let me get my. The acceleration of the block is going to be in this direction. And rather than call it X or Y, I'm going to call it the parallel direction. And the reason why I'm calling it the parallel direction, because it's like a train track with the incline, because that's what's going to happen. The block is going to slide parallel to the incline down the incline. Does that kind of make sense, everybody? Yeah. As for the normal force is like through the thing. Now, I just want to make sure that it's perpendicular because it's kind of hard to tell when I'm just doing it like that. So I think this looks pretty close to perpendicular like that. Right. And change the coloring so that it's really light gray and very light. Let's line everything up so it all kind of agrees with each other. That looks right. So we got to fix the normal force ever so slightly. And I'm going to do something very specific, and you'll see later on why I do what I'm about to do, but it probably won't make any sense at first. So I'm going to just kind of, actually, I'm just going to get rid of it for now. I'm going to copy this, paste it here. So you can see to scale how everything sort of is connected. So I'm just going to take that like that, take a vector like so, from this line up to here. And that goes up to like so. So our normal force is going to point exactly like this. So this is our Fn, the normal force. Yeah? So far, so good. Any questions, comments, or wonderings about the forces acting on the block? No? Anything else acting on the block? Any other forces? We're good? Yes, Diana?
Is it called the force of tension?
Nope, no tension in this case. There's no, what's it called? No rope. Inaloy?
The applied force?
Nope, nobody's pushing it. It's just a block sitting on an incline. Aaron?
Isn't it the block itself?
How does the block push itself?
Like it's putting it down. I don't know, because I saw that it looked like 10 grams.
It's 10 kilograms, yeah, but the block, the 10 kilograms creates weight. So that's the FG.
Okay.
Fatima?
Is it friction? Or
Nope,
no?
it's a frictionless incline. The answer is, that's it, we're done. Just put down the pencil. You got it. These are the forces acting on the block. That's it, nothing else. Any questions? Well, this is lovely, and it is helpful to us and see that there are these two forces acting on this block. It doesn't really help us answer the questions. See, I put a couple of questions. The question was, what would the value of the normal force be? And how much acceleration would the block have? As it currently stands, this free body diagram is not good enough for us to find these values. I don't have any mathematical relationships here yet. For example, does the normal force equal the weight in this case? Green, it does. Red, it doesn't. Put it in the little response chat. Green, the normal force is equal to the weight. Red, the normal force is not equal to the weight. Yeah, most of you look like you're on the right track. There's a bunch of you that are just like, I don't know. It could be, it couldn't be. In fact, the normal force does not equal the weight in this situation. They are not equal to each other. And this is the reason why the block accelerates, because there's some unbalanced force left over since F net does not equal 0, the acceleration is going to be greater than 0, right? You're going to get some acceleration because there's some unbalanced force. So to solve this problem, what we're going to do is we're going to do something very similar to what we did yesterday, right? And I'll show you what I mean. So first, what I'm going to do is I'm just going to leave this as is. So if anybody ever asks, draw a free body diagram for the forces acting on a block on a frictionless incline, this is it. There should be no other forces because these are the only two forces acting on the block. So what I'm going to do is I'm just going to take all of this. Copy it. And we're going to bring it down one more and talk about how we can break this into something workable. All right. Copy this. Copy down here. Bring this back over to here so it helps us with our analysis. So how we're going to deal with this is we're going to do the same kind of thing we did yesterday, where when we talked about this, remember how we solved this problem? What I did was, instead of thinking of the whole force, I only used part of the force, the part that was in the x direction, the part that was in the same direction as the motion. Well, in this case, the same as the opposite direction to the frictional force, right? It was the forward direction. So we're going to do the same thing, but I'm going to do it with a weird force. In this situation, right, I'm going to break. See, the normal force is perfect. It's right on the perpendicular direction, right? This is the perpendicular axis. So the normal force doesn't need to be broken into pieces at all because we already know it's perpendicular to the motion of the object. It doesn't affect the motion of the object directly. This guy, on the other hand, our weight See how the weight, like some of it is in this direction and some of it is sort of like in that direction a little bit. It's like doing two things. The weight of the object is pushing the object into the incline, but it's also causing the object to slide down the incline. It's what's creating that motion that's accelerating the block. That kind of makes sense to everybody, concept-wise? Gravity is doing two things. Instead of just doing one thing, it's doing two things. So how we break it down is as follows. Just erase this thing. So what I'm going to do is I'm just going to use this for guidelines, but we don't really, they're not going to stay. They're just there to help me make sure I don't get the, take this guy, place it right like so, right? And I'm going to take this perpendicular one, place it like so, crisscross right there, right? This allows me now to project the weight onto the perpendicular axis and onto the parallel axis. So to project it, I'm just going to take the part of this arrow, that's in that up to that direction. So what I'm going to do is I'm just going to take an arrow here to here, and we're going to call this one FG parallel. Question? Yes, Vincent?
The arrows represent the parts of FG, right?
Yes,
So,
it's
like,
a
we split up-
part of the force of
Okay.
gravity. It's not a new force. This is not some magical, mystical force from someplace else. It's just a part of the force of gravity. This does not belong on a free body diagram of forces because it's not a separate force. It is part of the force of gravity. Does everybody understand what I'm saying here? It's not the whole thing. It's just a piece of gravity, right? In the same way, I could take this part and project it onto the perpendicular axis, and I get an arrow that looks like this, down to here, like so, and I call this FG perpendicular, right? Depending on who's teaching it, sometimes they'll call this X and Y. I don't like using X and Y because it's confusing between, normally we think X and Y are vertical and horizontal and vertical. I like parallel and perpendicular because it's pretty clear that what each thing's doing. Parallel is the force that's driving the block to slide it along, and perpendicular is the force that's pushing the block into the incline. Questions about this so far? Vincent, did you have another question or did you just forget? There you go. Okay. Now, once we got that all lined up, the rest of it just becomes a smidge of mathematics. So here's how we're going to do. What I need is I need a relationship between these three forces so I can calculate whichever I need. Because if you can see, what is the relationship between the normal force and the perpendicular component of gravity? Anybody see it? Just from the diagram? Raise your hand so I know who's talking. Fatima?
Aren't they the same?
They're the same, yes. In this situation, and in fact, this is in general, and I'll show you why it works every time. The normal force is always going to be equal to the part of gravity that is perpendicular to the incline. If the incline was flat, right, if it was a flat incline, well, all of FG is perpendicular, right? Because it's literally going through the surface at a right angle. So all of gravity would be perpendicular, so it turns back into the one that we talked about before. But in all cases, the normal force is equal to the part of gravity that's perpendicular to the surface, right? So far so good. So we got that. If we could find some relationship to find this perpendicular component, we've figured out the normal force. And if I want to find the acceleration, this is the unbalanced force because there's nothing over on the other side. So all I got to do is find the parallel component, and I'll be able to find my acceleration. Does everybody understand the goal in this case? All right, let's do some geometry. Yay, geometry. We love geometry. Fun with shapes. Everybody loves shapes. All right, so here's what I'm going to do. I'm just going to do some basic vector manipulation, right? Vector manipulation. And how I'm going to do this, I'm just going to steal the arrow right out of the diagram, right? I just got a little arrow. I just stole it from the diagram. Sorry, my voice is killing me today. It's like, I've been talking too much lately. So this is called FG, right? And then I'm going to steal this one and place it down over here like so. Right. Call that FG perpendicular. And lastly, steal that blue one. Now, in the diagram, I had the blue one up here. But the great thing about vectors is you can move them anywhere you like, as long as you keep the length the same and the direction you don't change. So instead of putting it up here, I'm just going to slide it all the way down so that it's down over here. And this is FG parallel. Everybody follow along so far? Any questions? Okay, so that's part of the puzzle. So I rearranged it so it looks like that. Now the other thing I've got to do is I've got to create some connection between this angle, the angle of the incline, and the relationship in this triangle. And actually it's not too hard to do if I overlay it. So here's what we're going to do. I'm just going to drop in this over here. I'm going to drop this down over here. And all I've done is I'm just moving things around a little bit, but not changing angles. So I'm putting that to there. And I'm putting this like so. This way we can work out the angle relationship, right? This is it's a geometry problem straight right now. So here's how it's going to go, right? I'm going to call this theta, right? I'm going to call this phi, and I'm going to call this angle up here x. And the reason why is I want to make a relationship. I want to establish the relationship between this angle up top and the angle that's down over there in the corner. Those of you that are good in geometry, you already know what the relationship is, but if you're a little rusty on your geometric proofs, we get to experience a fun geometric proof together. Yes? I see the excitement in your face, Aaron. You look ready to go. She's like, yes, triangles. So what is the relationship if I add theta plus phi plus this angle in the corner? What is theta plus phi plus 90? What is that going to equal to? Vincent. Sorry.
It'll give us 180.
180. Yeah, 180 degrees, because there's 180 degrees in a triangle, and those are all the triangles. So I can rearrange this without too much extra math and write that theta is equal to 90 minus phi. Is anybody confused on why that's true? I just subtracted 90 from both sides and then minus phi from both sides, and I get 90 minus phi. Right? Okay, what's the relationship between phi, if I add phi and x? What is that going to equal to? Diana?
I think I forgot to lower my hand, but I think it should be 90 degrees.
That's correct, right? If you look at the corner here, this is a 90-degree angle that's shared if you add theta, phi, and x. So it's 90 degrees. So if I get x by itself, I get x is equal to 90 minus phi. So can anybody tell me what the relationship is between theta and x? Who can see it? Inaloy?
They're the same.
They are the same. If theta is equal to 90 minus phi and x is 90 minus phi, since they both equal 90 minus phi, we can make a very clear proof that x is equal to theta. And this then allows us to use the incline angle to solve for the pieces of the puzzle that we need. If we think about it now, let's make this nice and clean. Copy, paste it over here, copy, paste it over here, copy. Let's reassemble our triangle now with all the pieces of the puzzle. This guy comes up to there, right? Like so. This guy comes down to here, like so. Now I know from the geometry of the situation that this top angle, the angle between the weight and the perpendicular component of the weight, this angle here is the same angle as the angle of the incline. It's theta. And this long side is FG. It's the weight of the object equal to M times G. And this one down on the bottom is FG parallel. That's the part that pushes the block down the incline, the weight. And then this one over here is FG perpendicular. This is the part of the weight pushing the block into the incline. With a touch of trigonometry, we can solve for each of these key sides, the parallel and the perpendicular part. We can write it as sine of theta is opposite over hypotenuse, and cosine of theta is adjacent over hypotenuse. That's nothing new, right? You guys have seen this before? I hope you have. In this particular triangle, the opposite side is the side that's across from the angle, so I'd label this the opposite side. The longest side, which is also across from our perpendicular angle, our right angle, is the hypotenuse. And this side, which is next to the angle, but it's not the hypotenuse, we call that the adjacent side of the triangle. Is that okay with everybody? Yeah. All we got to do then is just replace it and do a little rearranging. So we can write the sine of the angle is the opposite side, which in this case is FG parallel, divided by what the hypotenuse is, and the hypotenuse is FG. The cosine of the angle is the adjacent side, and the adjacent side you can see is FG perpendicular. So I'll leave that as FG perpendicular, divided by the hypotenuse, which is FG. To get FG perpendicular and parallel by himself, I'm just going to multiply both sides by FG, and I'm going to flip them so they're on opposite sides. So it'll become FG parallel is equal to FG sine theta, and FG perpendicular is equal to FG cosine theta. These two equations, super, super, super important. There's a couple of reasons why they're important. For one, they're a quick way for you to figure out the part of gravity pushing something down an incline versus the part pushing it into the incline. For two, it's not on the reference table. So you're going to have to memorize these. You have to know them, right? Or you could just look at the trig and work it out from the triangle. It's really your choice. I used to memorize it. I would say, sine goes down the incline. That kind of helped me remember it. Like I just remembered it as like it kind of rhyme, sine down the incline. And it's tricky because usually cosine is the thing that goes horizontally. In this case, they swap because of the nature of the angles. Yeah? Questions about any of that? Now we can see exactly why, how how to solve for the pieces of the puzzle, right? If I want to find the normal force for this case, for example, I would write that the normal force Fn is equal to Fg perpendicular, right? So you can write that's equal to Fg cosine theta. So for this case, it'll be Fg, which is m times g times cosine theta. So the mass was 10 kilograms times it by g, which is 9.8 newtons per kilogram, times the cosine of 30 degrees. So throwing that all into your calculator, we get 10 times 9.8 times cosine of 30. We get 84.9 newtons is the normal force. And you can see how it doesn't equal what you would expect for the full weight. The full weight's close to 100. Vincent, did you have a question, or was that hand raised from before?
My bad.
That's okay. Now the acceleration part is a little bit tougher, but it's not too hard. We know that acceleration is equal to the net force divided by the mass, right? That's just Newton's second law, right? In this case, what is the net force acting on the block? What part is unbalanced? Someone raise their hand if they can identify it. Nobody, huh? Let's look. Which arrow in this picture is not balanced by something on the other side? Someone I haven't heard from today. Let's go with Pauline. Which one is not balanced?
I'm not sure.
Okay, if you look at those arrows, which one doesn't have an arrow on the other side canceling it out?
For the force of gravity of the
It's one of the forces of gravity.
parallel.
Yes, you can look at this when you see, right? This arrow doesn't have anything on the other side. That means it's unbalanced. So in this situation, we can write that the net force, F net, is just equal to the parallel force of gravity. Now, this wouldn't be true if there was friction involved. If there's friction involved, you have to deal with friction as well. But for this case, because we're doing a nice simple one where there's no friction, the parallel is the only force you got. So we can go back up to here. And then I can write that the net force is just Fg parallel divided by the mass, right? Which is equal to Fg parallel, we said was Fg sine theta divided by the mass. But there's something very interesting that happens when it comes to the acceleration. If you look, it becomes the acceleration is equal to, well, Fg is just m times g times sine of theta divided by the mass, right? But there's an m on top and there's an m on bottom, and so that just means they just cancel each other out because you're dividing it by itself. So you find that the acceleration down the incline is just g times sine of theta. Acceleration equals g sine theta. This is the acceleration for any object going down a frictionless incline. Block on. And it's weird because it doesn't matter what mass block you put on a frictionless incline. If it's a 20 kilogram mass block or a 100 kilogram mass block, it has no effect on the acceleration. But when you think about it, it's actually not that crazy because what happened when we dropped a bowling ball or we dropped a feather in a vacuum? Anybody remember? Hopefully you remember. Steve?
In a vacuum, both of them would land in at the same time.
Yeah. When gravity is the only force acting on an object, the mass of itself doesn't have any effect on the acceleration of the object. Yeah? Questions, comments, or wonderings about anything involving the inclined plane? I'm gonna stop the recording now, so.